Jai Hind everyone. I am Dr. Suman Gotwal, working as an assistant professor in the Department of Mechanical Engineering at AKGEC Engineering College, Ghaziabad. So today, the topic of discussion is linear programming. Okay, so linear programming is used in operation research, and here the code is written MTME102. That is for the MTech first year students. But we are studying the operation research in the BTech fourth year also. So the targeted students here will be the BTech or MTech students. So in today's lecture, we are going to discuss about the linear programming, how the linear programmings are formulated and how we can find out the solution using the graphical method. Now we will discuss about the outline of today's lecture. First, we will see what is linear programming and what is the requirement of this linear programming. Then we will see or discuss different components. After that, we will see how we can formulate the LP problems. Formulation is basically converting the descriptive statements into the mathematical form. So, how we will formulate the LP problems, we will discuss in the coming slides. Now, after that, we will see what are the assumptions that will be made during the LP model. Then we will see how can we write the LP in the mathematical forms and what is the standard form of writing the linear programming problems. Then we will see about the LP model formulation with the help of an example. Then we are going to discuss the graphical method, means how we can solve the linear programming with the help of the graphical method. And in last, we will see about the classification of different solutions. So first is the linear programming and overview. Basically, this technique is used to find a solution for optimizing a given objective. And here the objective can be maximizing the profit or minimizing the cost. Okay, and the objective we can see here that the objective of business decision frequently involve either maximizing the profit or minimizing the cost. Clear? So in this case of linear programming, the objective functions and the boundary condition all will be linear in nature. Okay, and this techniques is used basically to allocate the resources in an optimal manner. Okay, in problems of scheduling product mix. So if we see the programming, so programming is basically the planning. Planning means the process of determining a particular plan of actions from several alternatives. And the word that is linear. Linear means all the relationships which are involved in a particular problem are linear in nature. So this is the linear programming. Clear? Now we come to the model components. So there are different components which are associated with the linear programming. First, we will see the decision variables. So what are the decision variables? These are basically the mathematical symbols which are representing the level of activities of a firm. Means different types of activities are involved in a firm. So what is the level of these activities? These will be decided by the decision variables. Then we have the objective function. So what is the objective function? Objective function is a mathematical relationship which is describing and the objective of the firm. Means whether we want to maximize the profit or minimizing the cost. Okay, this is the objective of the firm. In terms of decision variables. Okay, means different activities which are involved in the firm. This function is to be maximized or minimized. Next component is constraint. Constraint is basically the requirement or restrictions. Okay, these are the requirements or restrictions which are placed on the firm by the operating environment. Okay, these are the restrictions, and under these restrictions or by satisfying these restrictions, we have to achieve our objective. So What is the constraints? Constraints are the requirement or restrictions which are placed on the forms by the operating environment stated in linear relationship of the decision variables. Okay, and the last one is the parameters. Parameters are basically the numerical coefficients or constants which are used in the objective function and constraints. So some constants or some coefficients will be used in the decision variable in the constraints as well as in the objective functions. These will be the parameters. So these are the components which we will use during the linear programming problems. Now we come to the formulation of LP problems. How we will formulate our problem, how we will convert or write the descriptive statement into the mathematical form. So we can see here, writing the descriptive problem statement into the mathematical form is known as the problem formulation. So there are some steps. So we will move step by step for formulating of LP problems. So first we have to clearly define the decision variables. So the first step will be to define the decision variables, means the different level of activities which are taking place in the organization. We have to define those. After defining the decision variable, we will construct the objective function. Means what is the objective of the firm, whether they want to maximize the profit or minimize the cost. So we will construct our objective function. After constructing the objective function, we will formulate the constraints. Constraints are basically the requirements and or the restrictions, okay, which are on the form, which are implemented on the form. So we will formulate these constraints, and the last we will define the non-negativity restrictions. Okay, so the decision variables or the objectives which are involved in our linear programming programs. So we will define here the non-negativity restrictions also, means these will always be positive in nature. Alright, okay, these can't be the negative. After that, we come to the assumptions that are made during the formulation of the LP model. First one is the proportionality. Proportionality is basically the rate of change of the objective function and the constraints equation is constant. Okay, the first assumptions that is made during the LP model is that the objective function, the rate of change of objective function and the constraint equation will be constant. Additivity means the terms in the objective function and the constraint equations must be additive. Okay, these will be additive in nature. Okay, whatever terms we are using in the objective function or the constraints, these will always be additive in nature. Then next assumption is the divisibility. Divisibility is basically the decision variables can take on any fractional value and are therefore the continuous as opposed to integer in nature. Means whatever decision variables are involved in our LP model or whatever the level of activities that are taking place in the organization, then can take any fractional value. Means these will be continuous in nature. Okay. Then certainty. Certainty means the value of all the model parameters are assumed to be known with certainty. Non-probabilistic means the constant or the parameters, the constant or the numerical coefficients which we are using in the objective function or the constraints, these will be known in advance and these will be certain in nature. Okay, so these are the assumptions of LP model. Now we come to the standard form of LP. So what we do in the standard form of LP, basically in order to find the value of n decision variables x1, x2, x3 to up to xn to maximize or minimize the objective function. For example, in this example we have taken n decision variables and these and decision variables are x1, x2, x3 up to xn. These are the n decision variables, and our objective function is basically z. Z is defining our objective function, which can be either to maximize or minimize. Okay, so we have written the objective function like this. These are the constant, numerical constant. So the C1 into x1 plus C2 x2 plus so on Cn xn. So this is our objective function. Then we will write down the constraints. So constraints are basically these are the n constraints. Okay, so constraints are a11 x1 plus a12 x2 plus a13 x3 plus up to a1n x1 is equal to b1. So in this form we will write down the constraints. So our objective should satisfy the constraints. Okay, there are m constraints here. Okay, and this x1, x2, x3 up to xn should be greater than equal to 0. Basically, this is the non-negativity restrictions. Okay, we are defining the non-negativity constraint. Means all the decision variables which are involved in this particular problem, LP problem, will be additive in nature or will be greater than equal to 0. Now we have taken one example here. Okay, one more thing I would like to tell you about this. If we are having the n number of equations with the n variables, then we will get the unique solution. But if the number of equations are greater than or less than the number of variables, then we will have the trial solution. Okay. Now we come to this example. So in this example, basically the product mix problem, it is the product mix problem. So it is saying Viva Creek Poultry Company is there, and which is manufacturing the two components, bowls and the mugs. So it is asking how many bowls and mugs should be produced to maximize the profit for given labor and clay constraints. Okay, product resources, requirements and the unit profit are given below. Resources 40 hours of labor per day, availability is 120 lbs of clay. So this is the example. So in this we can see here that the company is producing two components, bowls and the mug, and the constraints are given in terms of the labor and clay constraints. Okay, so here we can see in this table resource requirement, labor hours per unit is 1. Okay, and for the bowl, and the clay in lbs per unit is 4, and here the profit is given in dollar per unit is 40, and similarly we can see it for the mug also. Okay, this is given, and the availability of means maximum amount of clay that is available with us is 120 lbs, and the resources means the labor is available for, or labor can work 40 hours per day. Okay, this is given. So this is the descriptive statement which is given to us, and we want to formulate our problem. So we have to convert it into the mathematical equation. So how will we do it? First, we have to define the decision variables, means level of activities which are taking place. So the company is asking how many bowls and mugs should be produced to maximize the profit. So in this line, we get to know that it is the problem of maximizing. Okay, we want to maximize the profit, and we have defined the decision variables here, that x1 is basically the number of bowls to produce per day. Okay, and the x2 is the number of mugs that should be produced per day. So we have defined the decision variables, and after that we have constructed the objective function. Objective function is basically maximize Z. Okay, Z is denoting the objective function. So we want to maximize Z. Now this 40x1 plus 50x2. So x1 is the number of balls produced per day and x2 is the number of mugs to be produced per day. 40 is basically this is the 40. So this is given here. The 40 is the profit for the balls and the 50 is the profit for the mugs. Okay, so this term 40 and 50 come from here. So we can write down our objective. Now we will construct the equations for the constraints. We will write down the constraints. Okay, so constraints, how we will do it? 1x1 plus 2x2 less than equal to 40 hours of labor. So first we are writing the constraint for the labor. So we will see from the data given, we can see here for the labor. So 1 into x1, the number of balls that are produced per day, 1 into x1 plus 2 into x2. Okay, 1 into x1 plus 2 into x2, and the maximum availability of labor is 40 hours. So this is the maximum term. So our constraint will become 1x1 plus 2x2 less than equal to 40. 40 is the maximum limit. So the symbol will be like this. 1x1 plus 2x2 less than equal to 40 hours of labor. So this is our first constraint. So next constraint will be for the mug. We'll see here that here it will become 4x1 plus 3x2. 4x1 plus 3x2, and the maximum availability of clay is 120 lbs. So this is the maximum value. So it should be 4x1 plus 3x2 less than equal to 120 lbs of clay. We can see here this. So these are the two constraints. Okay, then we will write down the non-negativity constraints, means all the decision variables which are involved here are non-negative in nature or which are greater than or equal to 0. So we will define it like this: x1 greater than equal to 0 and x2 greater than equal to 0. Okay, so this is our formulation. Now we will write down the final formulation like this: maximize Z is equal to $40x1 plus $50x2, and which is subjected to these are the constraints: 1x1 plus 2x2 less than equal to 40, 4x1 plus 3x2 less than equal to 120, x1 greater than equal to 0, x2 greater than equal to 0. So this is the formulation of LP model. So in this manner we can formulate our LPP problems. Now we will see how we will find out the solution. So this was only the formulation of problem. We have formulated the problem, but we have not find out any solution here. So for getting a unique solution, we will use a method that is known as the graphical method. So there are some steps involved in the graphical method. First, what we will do, we will consider each inequality as an equation. So we have seen during the formulation of the LPP that the constraints are in the form of the inequalities, either the greater than equal to or less than equal to. The first step will be to convert the inequality into the equations. We use the equal to signs, or we will convert the constraints into the equations. After that, we will plot each equation on the graph. Okay. For example, if we have 3 constraints, then we will get 3 equations and we will get 3 lines. Okay. So we will plot each equation on the graph. After that, we will shade the feasible region. Okay. So what is the meaning of the feasible region, or how we will decide that what area is to be shaded? So if this symbol is associated in the constraint, we have this symbol less than equal to, then we will shade the region which is below the line. But if the symbol greater than equal to, okay, is in the constraint, then we will shade the region which is above the line. Okay. After shading the area or the feasible region, we will select the points which are lying on the common region. Okay. We will select some points which will lie on the common region. After that, shade the common region. Okay. Then we will select the point where the objective function is maximum or minimum according to given problem. Okay, so these are the steps which we are going to follow during the graphical method. Now we have taken the same example which we discussed during the formulation of the LPP model. Okay, so we have taken we have discussed this already, that how we can formulate our LPP models. Okay, so our objective function was to maximize Z is equal to $40x1 plus $50x2. X1 was basically the number of balls that must be produced per day, and X2 was the number of mugs which should be produced per day, and this was the 40 and 50 was the profit per day, and we want to maximize our profit. So this was our objective function. Now it was subjected to the constraints. Okay, these were the constraints. Means the 40, there were two constraints in our previous example. The first one was the labor, and the second one was the clay. Okay, these were two constraints, and the maximum limit means 40 hours. 40 hours were given for the labors, and this availability of this was 120 lbs. Okay, and using the these and the other data which was given, we had written the constant 1x1 plus 2x2 less than equal to 42 and 40, and 4x2 plus 3x2, 4x1 plus 3x2 less than equal to 120. These were the two constraints, and x1 greater than x1 comma x2 greater than equal to 0. So these were the non-negativity constraints. So this is our problem. Now we are finding a solution with the help of the graphical method. So we will plot a graph. X1, this x-axis is, or horizontal line is showing the x1. X1 was the number of poles. Okay, and the x2 is the vertical line on the y-axis, that is the number of mugs. Okay, so our first step during the graphical method was to convert the inequalities into the equations. So what we will do, we will convert it into the equations. So if we convert it into the equation, it will become x1 plus 2x2 is equal to 40. Okay, and we will plot this equation onto the graph. So we will get the two coordinates x1 40, and x2 20. Okay, we have plotted this line here. Clear? In this, similarly, we will plot for the second constraints also. So in the second constraint will become 4x1 plus 3x2 equal to 120. Okay, we will find out the value of x1 and x2. Okay, x1 comes out to be 30, x2 comes out to be 40. So we will plot the second equation also. So we can see here we have plotted. Now if we how to shade the area. So the next step was to shade the feasible region. So if we see for the first line, this less than equal to symbol is involved here. Okay, so it means we will shade the region which is below the line. Okay, means this area will be shaded. Clear? And in this case, here the less than equal to symbol is involved in this equation. So in this constraint, so we will again shade the area which is below the line. Okay. Now we will plot both the lines on the graph. So we can see here, and we will select the common region, or we will find out the common point. So we can see we get the 3 points. Okay. One is on the x1, the another one is on the x2, and one is the intersecting point. Okay. So we know the coordinate at the x2, we know the coordinate x1, but we have to find out the coordinates at the intersecting point. So we can find out using these two equations. Okay. So we will find out the coordinate of this. So like this, we will write down the equation x1 plus 2x2 is equal to 40, and 4x1 plus 3x2 is equal to 120. Clearly, and we will solve these equations and we will get the coordinate of this particular point. Okay, this is the common region. Okay, we will get the solution here. So this B point. Okay, this is A, B and C. We want to find out the coordinates of point B. So the coordinates are 24 and 8. Okay, 24 and 8. Now we have all the coordinates. Now what we will do, we want to find out the profit. So that means we want to find out the number of balls or the mugs that should be produced to maximize the profit. So what we will do, we will put these coordinates into the objective function, and we'll find out the value of z. So x1 was 0 here, x2 was 20, and we get the value of z objective function as $1000. And here the x1 was the 24 balls and x2 was 8 mugs. Then we get the value of z as 1360. And when the value of x1 was 30 balls and x2 was 0 mugs, we got the value of z as the $1200. So we can see here that the value of z is maximum when the coordinates are 24 and 8. It means the 24 balls should be produced per day and 8 mugs should be produced per day to maximize the profit. So this is our solution. Okay, so this is all for today's lecture. Thank you very much.